All right, so let's start. So welcome everybody to the Western Hemisphere Colloquium on Geometry and Physics. I'll remind you that during the talk, if you can stay muted, but if you have questions, please type it into the chat. And after the talk, you can use the raise hand button to indicate, and then you'll be able to ask your question. So we're very happy today to have Sourav Chatterjee from Stanford University talking about strong mass gap implies quark confinement.
Okay, thanks, Dan, for the invitation. It seems like a very nice series of seminars, so I'm honored to be here. So Dan told me that the audience here will be more or less knowledgeable in physics, and so I don't need to motivate much of the physics. I'll still say a little bit, just in case there are some people here who don't know the terminology. So let's see. Okay. So quantum Yang-Mills theories are the constituents of the standard model of quantum mechanics. So this describes interactions between elementary particles. Just a minute, let me organize my screen. Okay, so and lattice gauge theories are discrete Euclidean versions of quantum Yang-Mills theories. So they're discrete and they're Euclidean, so you have to do a weak rotation to get the quantum theories. And so I'll not go into the details of that, how you would want to go from lattice gauge theories to quantum theories. And just to begin, lattice gauge theory may be coupled with some fields, such as a Higgs field, or it may be a pure lattice gauge theory. And in this talk, we'll only deal with pure lattice gauge theories. Okay. And I'll define everything, so don't worry. I'll define everything that I've written down here. A pure lattice gauge theory has some components. So one is what is called the gauge group, and this is, there is a slight difference in terminology between what mathematicians call the gauge group and physicists call the gauge group. So for physicists, the gauge group is just a group associated with the theory. So it's a compact matrix Lie group. At the dimension of space-time, which is usually, the most important case is d = 4, and the parameter known as the coupling strength. So pure lattice gauge theory just depends on these three components, and you tie them together to build the theory. And these theories are important. These are not just toy models. So these theories on their own, even without passing to a continuum limit or constructing the quantum field theory, these can yield substantial physical information and about elementary particles and the interaction and the forces, the masses. And they're actually, huge supercomputers running all these calculations, for example, in CERN, so it's a huge business. So if you look at, the literature on this, so it's called Lattice QCD. So there is this whole area called Lattice QCD, where they do this kind of calculations just using lattice gauge theories. Okay. Now, there are two important questions about lattice gauge theories. There are more, but there are two very basic questions which are still not answered. One is mass gap. So it's the Yang-Mills mass gap problem. And in lattice gauge theories, this mass gap is equivalent to exponential decay of correlations. So if you can prove exponential decay of correlations in lattice gauge theories at weak coupling, so there's this coupling parameter which can be big or small. So weak coupling is a small value of the coupling parameter. That would be a huge deal. So that would be a huge step towards proving the Yang-Mills mass gap. So it's a statistical mechanical model, and you have to prove exponential decay of correlations. Okay. And this has not yet been proved in the most important cases. And there are huge Monte Carlo studies, and also there's this physical heuristics based on renormalization group, which indicate that this conjecture is correct, this exponential decay of correlations, and give correct physical predictions. So you can actually calculate masses of elementary particles by looking at the rate of decay of the correlation, so the constant and the exponent. And people actually do that with many different kinds of elementary particles which I've never heard of. So there are these studies where people do simulations, and they try to get these masses, and apparently they match up to 90% accuracy or something. The second big open question is the question of quark confinement. So quarks are what make up protons and neutrons, so these particles, and it's a mystery why quarks are never observed freely in nature. So this has received a lot of attention, and there's a lot of contributions, but the current consensus seems to be that a fully satisfactory theoretical explanation of this does not exist. And Wilson in 1974 argued that quark confinement can be showed using a lattice gauge theory by proving what's known as Wilson's area law. And I'll talk about that more. So a number of deep results are known, but the main question remains open. So that's one of the things in this talk. So there are these two big open questions, the mass gap problem and the quark confinement problem. So this talk is about getting some kind of connection between these things. Okay, so just right away, the main, any questions? Okay. Yeah. Okay. So right away, the main result, well, I'll state it in a much more precise way later on, but just an overview. What I'll show is that if the gauge group is compact, connected, and has a non-trivial center, then the presence of exponential decay of correlations under arbitrary boundary conditions implies that Wilson's area law holds. Okay. So this non-triviality of the center is a very important thing. It's so the physicists realize that it's very important for the area law to have non-trivial center. So this is sometimes called center symmetry. And for example, if you have SO3 in the gauge group is SO3, which is a trivial center, it's supposed to not be confining. So it depends on the group, whether the group has a non-trivial center or not. And this is the first result which kind of makes this notion precise, like why is the non-triviality of the center important? Now, this exponential decay assumption that you have exponential decay of correlations under arbitrary boundary conditions, this is actually a little bit stronger than usual mass gap. So this is not very well known, actually. It's quite subtle. Usual mass gap means exponential decay under a specific boundary conditions that's dictated by the transfer matrix. Okay. And so what I mean here is that you need exponential decay under arbitrary boundary conditions as a statistical mechanics model, what we usually mean. And I'll tell you more precisely what that means. So that's why I call it strong mass gap. Okay, so this is the broad overview of the result, and I will go into more precise details soon. Now, here is a slide on the physics viewpoint on this whole thing. So this will not be fully satisfactory to a mathematician, because I'm going to talk about it in physical terms and sort of intuitively, but it's just a couple of slides. Okay. So there is a long-standing belief in physics working in the work, originating in this work of Truft in 1978, that mass gap plus unbroken center symmetry implies confinement. So note this unbroken center symmetry is not a rigorously defined concept. So I'll not go into the details of that, what this exactly means. So what you can say is that in the previous slide, the result shows a strong mass gap plus center symmetry implies confinement. Now, the physical explanation is that strong mass gap prevents the breaking of center symmetry. Okay, and I'm not sure if just mass gap will do that. In fact, there are some lattice gauge theories, not the main ones, but lattice gauge theories with finite gauge groups, where the gauge group has a non-trivial center, and it's believed that the theory is both gapped and non-confining. And the reason must be, in view of this result, which is a rigorous mathematical result, that in these theories there are some boundary conditions under which the correlations do not decay exponentially in these models. That's the only possible explanation for this. That is, they're gapped in the sense that the correlations decay under some boundary conditions, but not all. And these are quite exceptional. These are mostly, theories with finite abelian gauge groups, that kind of thing. And now,
can I ask a quick question, Sourav?
Yeah.
Yeah. So there's a question: how can you tell the difference between, for example, SU2 and SO3 in the absence of matter?
Well, I don't know. Yeah. So I think one of the ways it will manifest itself is through this quark confinement phenomenon. That is, if you have the area law, or whether you have the area law or not, whether it holds or not. So that's one way. It's supposed to manifest itself, but beyond that, I'm not sure how we can do that.
Okay.
Yeah. So so the one question is, again, this is the second slide on the physical intuition. So is strong mass gap valid at weak coupling? So the main interest in this whole business is this 4-dimensional SU3 lattice gauge theories, which is the theory of the strong force. And this is what governs the interactions between quarks. And this theory is supposed to be both gapped and confining at all coupling strengths. So that's what people believe. Now, since SU3 has a non-trivial center, our theorem says that if it has a strong mass gap at all coupling strengths, then it's also confining at all coupling strengths. And if this is true, then it would solve the quark confinement problem. So if one can prove that a strong mass gap at all coupling strengths, this theorem will tell you that it has area law. Now, the main question, of course, is does it have strong mass gap at all coupling strengths? And the answer is that I don't know. And all I can say is that, well, the evidence for mass gap is purely, heuristic. I mean, it's physical renormalization group-based arguments, and although even that, even the physicists don't think it's complete. There is a complete understanding of that, and so I haven't seen any result which says that, oh, this is true for mass gap, but mass gap is true and strong mass gap, no, we don't have that. So there's no particular reason to believe that one is true and the other is not. If you believe the heuristic, then so since it's not at the level of a rigorous proof, this is the most I can say about strong mass gap. So it would be interesting to see if one can prove actually strong mass gap for SU3. And there are some forthcoming results, so I'll add some more results. So I'll actually include a rigorous formulation of this conjecture that mass gap plus unbroken center symmetry implies quark confinement along with the proof. So I'll give that. And I'll also give a toy example, which is a modification of SUN theory, which exhibits strong mass gap at weak coupling. So those are for the future. Okay, so now to more concrete things, so this was all the big picture. So let me define the mathematical theory. So let n and d be two integers. And let G be a close connected subgroup of the unitary group, UN. Okay. Let Bn be a box, be a cube in ZD. Okay. So this is capital N and this is little n. So this is, you can think of little n as a fixed number. Capital N will send to infinity eventually. Let En be the set of positively oriented nearest neighbor edges of Bn. Okay. And let omega n be the set of all functions from En into G. So that is the set of all assignments of group elements to positively oriented edges. This is our space of configuration. So I'm trying to define a statistical mechanics model, and this is our space of configuration. So you have this cube and you have this positively oriented edges. Each edge can have two orientations, positive and negative, and then you attach a group element to each edge, and that's a typical configuration. Okay. And then when you have a configuration and E is a negatively oriented edge, we just define the group element attached to that edge to be the inverse of the group element attached to the positively oriented version of that. So that's the usual conventional lattice gauge theories. Okay. So if there's any question about this notation or something else, maybe I can start. I'm just going through the slides, but maybe I should stop a little bit.
No, I think there are no more questions.
Okay. Okay, so you have this setup, okay, and this is some notation that we will use. So you have this group, and you have the cube and the set of positively oriented edges, and you have the space of configurations. Now, Plaquette is a very important terminology in lattice gauge theory. Is a set of four direct edges that form the boundary for square. Let Pn be the set of all plaquettes in Bn. So it's just little 2x2 squares. Okay. So given a plaquette P and a configuration omega, we define the group element attached to the plaquette P as follows. So you write the edges of P in one after the other as E1, E2, E3, and E4. So these are directed edges. Okay, and then you define omega P to be the product omega E1, omega E2, omega E3, omega E4. And so there are some ambiguities in this definition about the choice of E1, which edge is E1 and the direction that you go. But this will not matter for us because we are only going to use this quantity, the real part of the trace of omega p, which is not affected by these. So if you choose some other edge to be E1 and you decide to traverse in a different direction, in the opposite direction, this real part of the trace is not going to be affected. Okay. So remember the group is a matrix group. So it's a subgroup of the unitary matrices. And then you define the Hamiltonian as sum over all plaquettes of this real part of trace of omega p, negative of that. So the minus is the usual physics convention. So I think in the paper I don't use that, but well, let's keep it here. And the pure lattice gauge theory on this cube Bn with gauge group G and coupling parameter beta is the probability measure mu n beta on the space of configurations defined as follows. So it's the product Haar measure on this group times e to the minus beta times this Hamiltonian, and then there's the normalizing constant. Okay, so that's the pure lattice gauge theory on this cube. So that's how it is defined. And here beta is 1 over g0 squared, so beta is positive, and g0 is the coupling strength. So beta small means strong coupling, the coupling parameter is large, and beta large means weak coupling, that is the coupling parameter is small. And then given a function, f on the space of configurations, the usual thing that we do in statistical mechanics is that we put this angle brackets f to denote integral of f with respect to this measure. Okay. So that's pure lattice gauge theory on a big box, and this is perfectly well defined. So the quantum gauge theories are supposed to be scaling limits of these theories, and that's what we don't know how to define. So that's the Clay problem of Yang-Mills existence, to actually show that these things have a proper scaling limit as the lattice spacing goes to 0, and you get a continuum theory out of that. How do you define the continuum theory and prove that it has properties that you can build a quantum field theory out of that? So all of that is part of the Clay problem. But the initial thing, defining this lattice gauge theory, is very simple. So it's a perfectly well-defined probability model. Okay, so let mu n, so now we talk about boundary conditions. So I just defined the theory without boundary conditions. Now let mu n be the lattice gauge theory defined in the previous slide. Now let del En denote the set of positively oriented boundary edges of this cube. And let del omega n denote the set of all functions from del En into G. So that's the set of all assignments of group elements to boundary edges. An element of del omega n is called a boundary condition. Let delta be such a boundary condition, then the restriction of mu n beta of this lattice gauge theory to the set of all configurations which agree with delta on the boundary is called the lattice gauge theory's boundary with boundary condition delta. So you take the original theory and then you restrict yourself to this. So basically, it's conditional probability, but I don't want to talk in that language. So you condition on the boundary to be equal to some given values, and then you get the lattice gauge theories with boundary condition delta. So it's just like any statistical mechanics model that we define. So we'll henceforth always assume the presence of boundary conditions. So we'll work with boundary conditions. Okay, so any questions up to here?
I have a question. Which boundary condition is the one that's the standard mass gap versus the strong mass gap?
Yeah, so the standard mass gap, I think it's probably the free boundary condition, because you want a transfer matrix, so you want yeah. So there's also this question of gauge fixing. So if you have the free boundary condition and then you fix one direction at a time, you can do gauge fixing and make all the edges in time direction to be identity. So you can make the matrix attached to the edges in the time direction to be all equal to identity if you have the free boundary condition. So the initial thing that I defined is the free boundary condition. You don't impose a boundary condition, and then you can do gauge fixing to make this all equal to the identity. And then it sort of just evolves like a Markov chain, on each spatial slice, and that gives you the. So I think it's a free boundary condition that corresponds to yeah, to the mass gap question. So I have to check. Yeah.
Okay, thanks.
Yeah. Okay, so okay, the area law. Let's talk about what's the area law, Wilson's area law for quark confinement. Let pi be a finite dimensional unitary representation of the group G, and let pi be the character of pi. And let L be a closed loop in this box with directed edges E1 to Ek. So the sequence of directed edges, you come back to where you started from. Now, given a configuration omega, the Wilson loop variable WL omega is defined as follows. So once you fix a representation, you just take omega E1, omega E2 up to omega Ek, just take the product along the loop, and then you take the character of that. Okay. And again, since the character would be the trace of pi, this will not matter, which edge is the first edge. The direction of traversal will matter, but which edge is chosen as the first edge doesn't matter over here. So lattice gauge theory is said to satisfy Wilson's area law for the representation pi if this Wilson loop expectations, the expectation of this variable under the lattice gauge theory is bounded by C1 times e to the minus C2 times the area enclosed by a rectangular loop. So you take a rectangular loop, and there's a well-defined notion of area, length times breadth, where these constants do not depend on this big N. Okay, so it do not depend on the box. So basically, the idea is that you want to take an infinite volume limit. So you can define a theory on the full lattice, okay, by taking capital N to infinity, and then you have it have that for every loop L. You have this kind of bound. So these constants can depend only on the group G, the parameter beta, the dimension D, and the representation pi, but not on N. Okay. So this is Wilson's area law, and this is a very strange thing because you are multiplying these matrices along a loop. Okay, so you can imagine. So these are all random unitary matrices. Okay, so once you pick a configuration from, so just speaking like a probabilist, pick a configuration from the lattice gauge theory, random configuration. So these are random matrices that you're multiplying, and these are random unitary matrices. So the whole product is a unitary matrix. And you can imagine that if correlations decay, then as you go farther and farther away, they become sort of independent. And so it's a product of many independent random unitary matrices. So you sort of expect to get something like from the Haar measure. And if it's exactly the Haar measure, the expectation is exactly 0, but it's not exactly the Haar measure. So you would guess that it decays like the perimeter. So the number of matrices that you're multiplying. So because you're going far away, the number of matrices you're multiplying, it will decay like the perimeter of the loop. And that is indeed true. So you can prove, not with great difficulty, you can prove under very mild conditions that this actually is bounded by some constant times e to the minus some other constant times the perimeter of the loop. That is not so hard to prove. But Wilson says something much stronger is true. It decays like the area of the loop, which is not intuitive at all. So why does this imply quark confinement? So here is the heuristic from physics. I don't have time to go into detail, so it's just one slide. Let VR be the potential energy of a static quark-antiquark pair separated by distance r. So they imagine it like that. So you have this quark-antiquark pair separating, and they're staying fixed in a static positions for a time t. And the calculations from quantum field theory for the continuous model, so not the discrete models, but for the continuum model, the quantum field theory calculations show that if you take a rectangular loop of side lengths r and t in the continuum limit of 4-dimensional SU3 theory and suitable representation pi, this Wilson loop expectation should behave like e to the minus VR times t, where VR is the potential of the static quark-antiquark pair. Okay, so if the area law holds, then it's e to the minus r times t. So it shows that if the area law holds, then VR should grow linearly in the distance r between the quark and the antiquark. And so by the conservation of energy, this implies that the pair will not be able to separate by more than a certain distance because VR is growing linearly. So you cannot have more than that. So that is roughly, very roughly. And this calculation, of course, I don't have time to present that. And the renormalization group arguments predict that beta has to be sent to infinity as lattice spacing goes to 0 to obtain the continuum limit. So that's why we need the area law to hold for large values of beta and not only for small values. So for small values, it is known. The main question is for large values, since we want to send to a continuum limit.
Sourav, I have a question. Can I ask a question?
No, but he can't hear you
Oh,
unless you.
That's good. Is there a discrete version of the quantum field theory calculations?
Not
Or
that
could there be, or should there be?
There could be, but I haven't seen one. So that's an interesting question. So that there could be the thing is, the discrete version, in the discrete version, you don't really have a quantum field theory. All you have is an Euclidean field theory. So in the continuum version, you go to the e to the I, you do the I there, and it goes to all these unitary operators and all that, and it's all based on that. So as long as you're not able to pass to that limit, so it's not clear.
I can change e to the t to e to the it if or in a finite sum. I'm not afraid.
Yeah, no, okay. So that is a possibility. So I haven't seen that. It's a good thing, that's a good thing to try.
Okay, sorry.
Yeah, no, I haven't seen that for lattice theories. Okay, so yeah, so it's all, the thing is, you take this lattice gauge theories, you have this continuum model, then you build a unitary operator out of that. So Hamiltonian becomes a unitary, it becomes a Hermitian operator, and take e to the IHT, and then you apply that, and then it becomes a calculation in terms of, sort of these Feynman diagrams, and to get this out of that. So, but it would be good to understand how that translates to the lattice framework. Okay. So here's some basic facts about the area law. It's easy to show that the area law holds that all beta in any 2D theory, since gauge fixing can be used to reduce any 2D theory to a 1D model. So that one can do. Although, if you have a complicated two-dimensional manifold, it can become a little more challenging. Zeiler in 1978 proved that an area law lower bound holds for any theory at any beta. So you can actually show that you cannot do better than the area law. So it's lower bounded by e to the minus constant times the area. There is a result of Simon and Yaffe from 1982 proving a perimeter law upper bound for the theory at any beta. And this is a sort of using the methods of mathematical physics, but you can also give a relatively simple proof using probabilistic arguments that the perimeter law upper bound should hold for essentially any theory at any beta. Okay. There are some deeper results. So Osterwalder and Zeiler showed that the area law holds at small enough beta for essentially any theory in any dimension. So if beta is small enough, then one can show, and this is using representation theory. It's not a simple proof, but it's it's a fairly general theorem. Now here are two very important results. So Alan Guth and Froelich and Spencer showed that in four-dimensional U1 theory, so if you take 4D and take the gauge group to be U1, the area law breaks down at large beta, and instead the perimeter law holds. So this is called the deconfinement transition. And this was physically expected because this is related to photons, which are not confined. So this was one of the things that was a little controversial in the beginning, that you have this lattice gauge theories which are supposed to describe confinement. So in fact, Wilson's paper was called Confinement of Quarks. So the whole purpose of defining lattice gauge theories was to understand confinement of quarks. Now physicists realized very soon that essentially any theory, this result of Osterwalder and Zeiler was expected. Any theory is confining at small beta, strong coupling. So how do you reconcile that with the fact that U1 theory is related to photons which are not confined, but this is also confining at small beta. So this was a breakthrough which showed that if you take 4D U1 theory and you take large beta, then actually the area law breaks down and you have the perimeter law at large beta. The only non-trivial case where I know that the area law has been proved, in a real theory, is this result of Goffert and Mack, who showed that the area law holds for all beta for three-dimensional U1 theory. So, unlike four-dimensional, if you go to 3D, this is still this only non-trivial case where the area law has been established at large beta. Okay. So these are some deep results. There are various other theorems which one should know. The Froelich showed that confinement in SUN theory holds if and only if holds in the corresponding ZN theory. There's a result of Durhaus and Froelich who showed that confinement in a d-dimensional pure lattice gauge theory holds if there's exponential decay of correlations a d-1 dimensional nonlinear sigma model. So I don't have time to define that. Then there are some other results of Borges and Seiler who proved confinement in lattice gauge theories at non-zero temperature. So there is also a temperature thing which you can put in, which is different from the beta. And there is a toy model, which is not a lattice gauge theory, a simplified thing, where you can actually do much more. You can prove a sharp transition from the deconfinement to reconfining regime by these authors. There is some recent progress. So this is all 40 years ago, but there is recent work also. So I have been working on this for a few years. So we can show area law at small beta for arbitrary loops in large N theories. Okay, not just rectangular loops. So the result of Osterol and Seiler was for rectangular loops. And here for arbitrary loops, the area enclosed is the minimum surface area. I also did this thing where I took 4-dimensional Z2 theory, and one can compute the exact leading order behavior at large beta as beta goes to infinity. So this was, with the aim of understanding this for more complicated groups. Of course, this is just Z2, the simplest possible group. And this has been extended to finite abelian groups by these authors and to all 4-dimensional theories with finite gauge groups by my student Sky Kao. And this is a very hard paper, Kao's paper, to all 4-dimensional theories with finite gauge groups. Now the question is, how do you, of course, generalize this to groups that are not finite? And that doesn't seem clear at all. Okay, so this is more or less the review of the things that are known about the area law. Okay, so now I'll state the main result of the paper in a more careful way, but any questions before that?
No, I think you can go ahead.
Okay. So here are the assumptions. So now that I have all the notation, I can tell you the assumptions. So assume that the center of G is non-trivial. And also remember we have a representation pi. So I have to relate it to this non-triviality to the pi also. And I further assume there is an element G0 in the center so that pi G0 is a constant times the identity for some constant not equal to 1. So pi G0 must be some constant times the identity, but I'm assuming it's a constant not equal to 1. So the image of the center under pi is also non-trivial, where I is the m by m identity matrix, m being the dimension of pi. Now the strong mass graph assumption, it takes some space here to say that. So say that two edges are neighbors if they both belong to some common plaquette. And say that a measurable map is a local function supported on an edge if f omega depends only on the values of the matrices attached to edges that are neighbors of this edge. Okay, so function of a few edges in a small neighborhood, that's a local function. And given two local functions, let dist fg denote the Euclidean distance between the midpoints of the supporting edges, some notion of distance between the supports of local functions. And the assumption is that there are positive constants k1 and k2 depending only on the gauge group G, the coupling strength, coupling parameter beta, and the dimension D, and not on the box, not on the size of the box that you're taking, not on n, or the boundary conditions, such that for any two local functions, sorry, this circle shouldn't be here, from omega n to -1, 1, you have the correlation, so the expectation of fg under the lattice gauge theory minus the expectation of f times the expectation of g, what in probability we call covariance and physicists call truncated correlation, is bounded by k1 times e to the minus k2 times the distance fg. So there is exponential decay. So there's a very precise sense in which you have exponential decay. You can define exponential decay in many different ways. So this is just one definition that I'm adopting. And the crucial thing here is that there is no dependence on this boundary condition. So no dependence on n is natural, because if it was allowed to depend on n, you could send n to infinity and not get exponential decay. K2 can be going to 0 with n. Okay, so not depending on n is fine, but not depending on the boundary condition is the critical thing. Okay, so these are the two assumptions. And under these two assumptions, this is the theorem. So let G be a compact connected subgroup of UN for some n, and let pi be a finite dimensional unitary representation. Take any dimension d bigger than or equal to and any beta in R, and consider the lattice gauge theory on the cube Bn with these parameters. Suppose that the center symmetry and strong mass gap assumptions are satisfied. So then there are positive constants C1 and C2 depending only on G, beta, pi, and D, such that the following holds. So you take any n and any boundary condition and any rectangular loop which is sufficiently away from the boundary. It's contained in a subcube Bn for some n prime less than n over 2. Then this Wilson loop expectation is bounded by C1 times e to the minus C2 times the area enclosed by L. And moreover, there is a unique infinite volume Gibbs state. If you're familiar with statistical mechanics, this will make sense. There's a unique infinite volume Gibbs state, and the above bound holds for any rectangular loop if the expectation on the left is taken with respect to this infinite volume state. Okay, so that's the main result. Okay. Any questions about this?
Oh, can I ask?
Yep.
On the previous slide, this constant K1. So they are fixed once and for all. These local functions can have arbitrary large support. It's only the distance between it that appears on the right-hand side.
The local functions, I call something a local function if it only depends on omega u for u that are neighbors of a single edge E. So a fixed, it can only depend on a fixed number of edges of the local function. So maybe the matrix attached to an edge and its neighboring edges. That's all it can depend on. And then this f and g are any two local functions, and the distance is the distance between their supports in some sense.
The edge E is fixed. There is one edge E that determines this class of functions.
No, so
I mean, arbitrary, of course, but
yeah, E is arbitrary, but yeah, the edge E is So the function has to be an edge. Yeah.
All right, thanks.
There's another question. Are we including boundary conditions which have a homotopy condition so that arbitrarily small solutions cannot exist in the limit?
I didn't quite understand what.
Okay, maybe we'll defer that for after the lecture then. We'll hold that.
I should ask at the end, but I mean, if you specify a boundary condition, which it's easier to see in a two-dimensional model with a U1 model, that you can force there to be a winding number around the boundary, so it's impossible to fill in the middle without there being large group elements in the center.
So you were talking about filling in, meaning that things which minimize the energy or something like that, right?
Yeah, right. So there's a lower bound on the energy just because of the boundary condition, and it has a homotopy in it.
Yeah. So that this is I don't have any such conditions. I'm just saying any boundary condition you put in, and on the cube.
Okay. Thanks.
Okay, so let me now go into the proof. So let me give you a broad idea of the proof. Let the first coordinate in this RD denote time, and let L be a rectangular loop with side lengths R and T, where the sides of length T are parallel to the time axis. So imagine them going up. Okay, and we wish to show that the Wilson loop expectation is bounded by e to the minus some constant times R times T. So it's not very difficult to prove, as I said, the perimeter law, that it's bounded by e to the minus some constant times R plus T. It's because essentially it's a product of R plus T matrices, and they're kind of independent as you separate them by distance. So from that, it's not very hard to show this. And combining with this information, we can show that it suffices to prove this, that the Wilson loop expectation is bounded by e to the minus some constant times e to the plus some constant times R plus T minus some constant times R times T. If we can prove this, then combining with this perimeter law, we can reduce this thing. So that, it's not very hard to do that. So we'll prove this one. Okay, so this is what we will aim for. Oops. Now, so you have this loop L, which is this rectangular loop. Okay, and there are these edges and on each edge there is a matrix, omega e, there's a random matrix, and pi of omega is another random matrix. Okay, pi is a representation. And and what you do is, let's take one element from each of these matrices. So just take some element, from each matrix, and let f be the product of these elements. So such a variable will be called a component variable. So note that the Wilson loop variable is a sum of some e to the some constant times r plus t component variables, because a trace of the product of these matrices. So you can do this. So it suffices to show that for any component variable, it's bounded by e to the constant times r plus t minus some constant times r times t. So this will be the r plus t will be absorbed in this, and then we can use the previous slide. So we'll just work with this, very kind of brutish thing that you just take this matrix and you take one element from each matrix, you take the product, and that's and then try to prove the area, this kind of a bound for such a variable. So what you do is you partition space-time into slabs of thickness L in the time direction. So L will be chosen later, depending on G, beta, and D. And let R be T over L. So L, think of L as a fixed but large constant. Then a component variable can be decomposed as a product of variables U, V times F1, F2, FR, G1, G2, GR, as in this diagram. So this thickened line, this box is your loop. So U is everything, the product of everything coming from the bottom line, and V is the product of everything coming from the top. And on the right and left, you have within slab 1, you have F1 is a product of things coming from the right side, and G1 is a product of things coming from the left side. So remember, these are all scalars. So you're just taking one element from each matrix, okay, fixed element from each matrix. So this component variable F can be written like this. Okay. Right. So then let omega be a random configuration from this lattice gauge theory, mu. Let mu prime be the conditional probability. Okay, I have to go into conditional probabilities. Given omega e for all e that belong to boundaries between the slabs. So what you do here is you take a configuration omega, and then you condition on omegas on the variables that belong to these boundaries between the slabs. Okay. So then let angle f prime denote the conditional expectation under this mu prime. Okay. So that the overall expectation is the expectation of this conditional expectation. The conditional expectation will be a function of these boundary values. So it suffices to prove the area law for this conditional expectation of instead of the actual expectation. Okay. So under mu prime, the nice thing is that this is a Markovian model. So the omega is inside one slab are independent of the omega is inside another slab. So the slabs become independent. The interiors of the slabs become independent as you condition the boundaries. So we get this identity. So the conditional expectation of f prime is u times v. So u and v, remember, are coming from the bottom and top, and these are from the boundaries. Now, F1 G1 is independent of F2 G2. So the expectation of F1 G1 and the expectation of F2 G2, the conditional expectation separate because of independence. But F1 and G1 are, of course, are not independent. But the slabs, the interiors of the slabs become independent because of the structure of the lattice gauge theory. So you get this identity. The conditional expectation breaks up as a product of conditional expectations times some things from the boundary. So this is a very probabilistic thing. So I hope everyone is following. If not, please ask.
What did you say were not independent? F1 and G1?
Yeah, F1 and G1 are not independent. So you see, once you condition on these boundaries, which are these lines, once you condition everything in the boundaries, the regions between the two slabs become independent. So everything inside this slab and everything inside this slab are independent of each other, but within a slab they're dependent. Okay, inside a slab. So F1 G1 as a pair, it's independent of F2 G2 and it's independent of F3 G3. But so when you take expectation here, you have conditional expectation. It becomes conditional expectation of F1 times G1 times the conditional expectation of F2 times G2 and so on. Okay. Okay, so you get this elementary sort of breakup of these conditional expectation. Now, so we want to show that this conditional expectation of f is bounded by this. So it suffices to show that each of these individual things, fi, gi prime, the conditional expectation is bounded by e to the minus c times r, since if you take the product of, so this little r is basically a multiple of t, so you get, and this L is a constant, so you get e to the minus r times t, so you end up getting this r times t over here. Okay. So this will be our goal, to show that this conditional expectation of fi gi. So remember, fi is the product of the group elements that you have chosen on the right side, and gi is on the left side, and we want to take the product of all of these and take the conditional expectation, and we want to show its exponential decaying in r. So remember, r here is this length over here, and t is this length. And so when you take the product of little r such things, so little r is a multiple of t, you get r times t. So now under mu prime, irrespective of the values of the omega is in the slabs, you have the conditional expectation of these individual things, fi and gi are 0. So this is where the non-trivial center comes in. So this is the consequence of the non-trivial center. So I'll not give you the proof. It's quite simple. It's basically due to symmetries. That even if you condition on the boundaries of the slab, the top and bottom boundaries, and you take group elements, so fi is the product of group elements along some string going up from the bottom to the top. And so that has expectation 0, and that is not necessarily true if G doesn't have a non-trivial center. So this is where the non-trivial center comes in. So to show that this fi gi expectation is bounded by e to the minus some constant times r, it suffices to show this, because these things are 0 anyway. Okay. Now this becomes a truncated correlation. So if you can show that these truncated correlations decay exponentially within each slab, then for any given, so if you can show that the truncated correlations decay within each slab for any given boundary condition, then our proof will be complete. And so the key idea is to show that this holds if the thickness of the slab is sufficiently large. So you have to take a sufficiently large, sufficiently thick slab, and then once we have that, we can show that correlations indeed decay exponentially within the slab from our original exponential decay assumption. So, so take a large but finite slab. Here, n is the size of the slab, which I called L before, sorry. So this is the, well, no, there is a reason. So this is minus n to n, anyway. So there's a large slab, but n is fixed and m is going to infinity. Think of m as going to infinity. The set of all boundary edges that do not belong to either the top face or the bottom face is called the, let's call the special boundary, because so top and the bottom denote time boundaries, and the other part is a special boundary. And consider lattice gauge theory on the slab with some given boundary condition. So we will show that the influence of the special boundary near the center is exponentially small in this m. So the boundary effect goes down, provided that n is sufficiently large, depending on g, beta, and d. So if the thickness is sufficiently large, then the effect of the special boundary inside the slab goes down exponentially in the size of the slab, okay, in the radius of the slab. So that's the idea. And this shows, this suffices to show exponential decay of correlation is a sufficiently thick slab. Okay, so I hope the main idea is clear. How do I get this area law? This is because of these things that you have this Markovian structure, and you have that you have exponential decay in a sufficiently thick slab. Also, you get that, and from this, and then using just this center symmetry, we can get this. And now, so how do you prove this? So that's the remaining question. So this is using coupling. So the proof goes using this technique of coupling from probability theory. So take any two boundary conditions on the slab that differ only on the special boundaries, not on the top or bottom halves, but bottom faces, but just on the sides. Two boundary conditions, and let mu and mu prime be the probability measures defined by these two boundary conditions. A coupling of mu and mu prime is a pair of random configurations omega prime, so that omega has law mu and omega prime has law mu prime. That's what is the coupling. So it's a pair of random configurations, so that one is from mu and one is from mu prime, but they're not independent. They're coupled together. So that their joint distribution is something that can be arbitrary as long as these two are satisfied. So what is typically done in this situation is to show that, to construct a coupling so that the chance of that the coupled variables omega and omega prime are different in some edge right in the middle of the slab is exponentially small in the radius of the slab. Okay, so the probability of omega e not equal to omega e prime is exponentially small in the size of the slab. Okay, so such a coupling is constructed in 3 steps. So this is again, so just for everyone who is still following up to here, so let me tell you the 3 steps in which this coupling is constructed. So first, we construct such a coupling with similar properties on a cube instead of a slab, using the strong mass cap assumption and the coupling characterization of total variation distance. So there are these things in probability that you can compute a bound on the total variation distance, and then using that you can construct a coupling on a cube. Now the connectedness of the gauge group is used in this step. So so we want to pass smoothly from one boundary condition to another. So that's where we use. Now, given any coupling on the slab, we update the coupling to get a better coupling. So what we do is we randomly choose a copy of a cube Bn. So remember, n is fixed. A copy of this cube Bn inside the slab. And then what you do is you choose a coupling first from the given coupling, choose a coupled pair of configurations, fix these 2 configurations outside the cube, and inside the cube, regenerate the values using the coupling from the first step. Okay, so here we are given any coupling of omega omega prime on the slab, and then you update the coupling using this procedure. We choose a random cube uniformly at random, and then we update the coupling inside this. And we show that the resulting pair is an improvement of the original coupling, and this improvement is quantified through an inequality. And so I'm almost done. So here is this inequality. So given a coupling, we measure the performance of the coupling at an edge E by the chance that omega is not equal to omega E is not equal to omega E prime under this coupling. And so this rho gamma E. So gamma is a coupling and E is an edge. So rho gamma E measures. So the smaller it is, the better the coupling. Now, given a coupling, suppose we improve it to gamma tilde using the procedure from the previous slide. So then we get an improvement in this rho gamma E. So let UE be the set of all edges that are at distance less than log n squared from E, and VE is the set of all edges that are distance less than n from E. And we get this inequality. Okay. Yes. So you don't have to really read this, but it's rho of gamma tilde E bounded in terms of rho gamma E and rho gamma U within these neighboring regions. And so then the step 3 is this updating is repeated an infinite number of times to get this vastly improved coupling. So you keep doing this repeatedly, this updating. And we apply this inequality again and again. So I'll just one more slide, I'll show you what we get at the end. And so this thickness has to be large enough is required to show that a certain parameter is strictly less than actually 1/2, which leads to the exponential decay. So let gamma n be a sequence of couplings produced by the successive improvements. And let gamma be a weak limit of this subsequence, gamma nk, then gamma is also a coupling. And then one can show that it's by standard results from weak convergence, one can show that rho gamma is bounded by this lim sup. And this lim sup, we now need to control this lim sup from this inequality. We applied the previous inequality to get this limiting inequality. And rearranging this, we end up getting this inequality, that PE is bounded by log n to the 2d over n times the maximum of PU over U in this neighborhood. So now you choose n large enough so that this is less than 1/2, which gives you this inequality. So now you see, this implies that there is some E1 in a neighborhood of E so that PE is less than PE1 over 2. And you can keep doing this as long as you don't reach the boundary. So we keep doing this until you reach the boundary, and that gives you this exponential decay. Okay. So anyway, that's the proof or a sketch of the argument. And so this shows this. And here's the preprint. I'll add some more results, as I said. And I want to thank Steve Schenker and Ed Witten for many conversations about this, in particular, clarifying this thing about, so there was some confusion in the beginning as to why I can have this exponential decay implies area law, even though there are some theories where it's believed that there is exponential decay. And it's because of this subtlety about, and that was, Edward really made that, clear. And so thanks to everyone for listening. Thank you.
I'll clap on behalf of everybody. Thank you for a beautiful talk. So if there are questions, please use the raise hand function and I'll unmute you.
Should I stop here now, or?
Pardon me?
Should I stop the screen share?
Well, you may need it for the questions, so you can keep it up. Marco, do you have a question?
Hi, thanks for the great talk. I'm just wondering, could you clarify or try to explain this thing about that chain between the slabs, the fact that that expectation was trivial because of the existence of the center?
Yeah. So the expectation, so what happens is that if you have a non-trivial center, you can do a transformation to the Hamiltonian, even if there are boundary conditions. Even if you have boundary conditions, fixed boundary conditions on the top and bottom, you can do a transformation of the Hamiltonian, which preserves, so a transformation of the configuration which preserves the Hamiltonian. So what you do is you take all time-like edges and you multiply all time-like edges by an element, a non-trivial element of the center, okay? And that will preserve the Hamiltonian because it will preserve every plaquette, okay? So that preserves the Hamiltonian, and therefore, the expectation remains unchanged, but the expectation, so that gives you the necessary symmetry. But the expectation should also be multiplied by the same constant, which is not equal to 1. So if the expectation remains unchanged by multiplying by a constant not equal to 1, the expectation has to be 0. You see.
So that's in fact the symmetry in center symmetry. When you say center symmetry, that is the symmetry.
Yeah, and the notion of unbroken center symmetry is the following. So it's the same like when you say unbroken symmetry in the Ising model, something like that. So what the physicist will tell you is that so okay, you have one line and the expectation is 0. If another line, the expectation is 0. But what about the product of the two lines? Does the expectation tend to 0 as the lines separate farther and farther away? And so there is this notion of Polyakov lines where this is language. It's very close to Polyakov loops or Polyakov lines. What I just said, and then you can. So that's when you say that the center symmetry is unbroken. That is, if you take two lines going farther and farther away and the expectation doesn't go to 0, then you say the center symmetry is broken.
Okay, thank you. Hank Chen has a question.
Yeah, hello. Hello, can you hear me?
Yes, go ahead.
Yes, okay. Yeah, I'm just wondering, like this very sort of probabilistic technique, I guess, for proving the decay of expectations. I'm just wondering, like, if we consider higher gauge field theories, can we generalize your technique to that context?
I suppose so. It's a fairly general technique, using couplings to prove decay of correlations has been used in the literature, not exactly in the form that I have done here. It's somewhat different, but there is a long history of using couplings to prove correlation decay. And it's a fairly general and adaptable technique once you can do it. For example, you can prove this Dobrushin's uniqueness theorem, that kind of Dobrushin decay of correlations, that kind of thing, using couplings. So, yeah,
like some sort of Lee Robinson type of bound.
I'm not familiar with that, but many of the things that you can do using, for example, these expansion techniques that you can also do using coupling.
Okay, thank you.
Thanks. Are there any more questions for Sourav? Okay, then let's thank Sourav again for a beautiful talk. And let me remind you that the next and the last colloquium in this series will be in 2 weeks on December 14th, and the speaker will be Harold Williams. So hope to see you then. Thank you.
Okay.
All right. Well, thanks. That was a terrific talk.
So,
I'm unmuted, yeah.
okay, so